All right, I would like a show of hands all around the class, wherever you are, sitting in the room right now. I don't care if there's people around. Raise your hand if you have owned a pool before. I am not raising my hand. I've never owned a pool. But uh, my family had a pool when we were growing up, so technically it was my parents' pool, and I was young enough they didn't let me handle any of this stuff, which is probably a good thing. But if you've ever had a pool and you were responsible for maintaining that pool, hopefully you checked the pH of the pool fairly regularly. If you didn't, then I'm glad you're still alive because there could be some really bad stuff happen if you let the pH of your pool get out of balance. But if you did, if you've ever done that before, it's very likely that you didn't really know exactly what you were doing. You just knew I stick this thing in the pool and it tells me what the pH is, and I know that this certain range is good. And that's all I need to know. Just if it's in this range, it's good. If it's in this other range, I need to add this to it. And if it's in this other range, then I need to add this to it to get it to where it's good. Didn't really explain the chemistry too much, which isn't necessarily a bad thing. You're not really concerned about the chemistry of the pool. If you're trying to get your pool to the right pH, you just want to swim in the thing. But we are now going to be very concerned with the pH. We are going to learn all about pH and how it is very useful to us in certain situations. So when we're dealing with the concentrations of H+ in solution, scientists decided that it was too much work, it's just too hard, to write out the entire concentration of the H+. That scientific notation, who needs it? Let's get rid of it. And the pH scale is born. The pH is defined as the negative base 10 logarithm of the concentration of hydronium ion, which is to say it is this. It is the negative log base 10, so this is not natural log. If you use the natural log, you will get the wrong answer. Those are completely different log scales. So it is the negative log base 10 of the concentration of H+. That is the pH. It is essentially just a way of writing very small concentrations without the scientific notation. Now, this P here at the beginning, P is commonly used as a mathematical shorthand for negative log base 10. That's why this is called the pH. It's the negative log base 10 of H, the hydronium concentration. And as we'll see later, there are a few other P scales that we will come across where the P stands for the same thing. It's just the negative log base 10 of whatever comes next. When we're talking about the pH of pure water, since we know that pure water has equal concentrations of the hydronium ion and the hydroxide ion, that tells us that the concentration of hydronium is 1 times 10 to the negative 7. And this is something that we discovered, so to speak, back here in this problem that we did, where we did this last section. So this, where H+ is 1 times 10 to the negative 7, that is neutral. And so that, if we plug it into the pH equation, so we plug it into this equation here, just plug 1 times 10 to the negative 7 right there, what we get is 7. That negative log base 10 essentially removes all the 1 times 10 raised to the negative, and you're left with just with 7. Now that is not going to work like that every time. If you have H+ concentration of 5.2 times 10 to the negative 3, you can't just be like, oh, well, I took the negative log, it's just 3. No, no. This is the only time where we can do that, other than if we have just 1 here. So it would actually work if we had 1 times 10 to the negative 2, that would actually be just a pH of 2. If the first number here is just 1, nothing else, just 1, then we can actually just take that exponent, as long as it is negative, and put it as the pH. but as a positive number. Sorry if I'm confusing you with that, but in general, it's always a good idea to go ahead and do the math. Don't just try to work it out in your head like that. So you might have already known that a neutral solution has a pH of 7. That's kinda, sorta known. That some people talk about that in their middle school and high school science courses. They'll talk about how pH of 7 is neutral. What you might not know is that if your pH is less than 7, that is what we consider acidic. It does not have to get down to 6. Anything less than 7. You could be 6.99999. Technically speaking, that is acidic. Anything less than 7 is acidic. Anything greater than 7 is basic. And I know that seems a little bit backwards. You know, if this is supposed to be a measure of how acidic something is, shouldn't the larger numbers be more acidic? This is just how the math works out. The way the math works out is that the larger the concentration, the smaller that pH number is. And to the point where you can even have negative pH values, as we'll see later. So when we're considering just any solution in general, if it is perfectly neutral, it will have exactly the same concentrations of H plus and OH minus, which would be 1 times 10 to the negative 7, and they would have to be these concentrations. You will never, ever, ever have an aqueous solution, a solution with water in it, that has, for example, 1 times 10 to the negative 5 H plus and 1 times 10 to the negative 5 OH minus. It's not physically possible. It can't happen. It wouldn't be an aqueous solution. It's possible to make a solution like that that's not aqueous, I would assume, although actually I'm not even 100% sure that's possible. But I am 100% sure that we will never see a solution like that. The only situation where the two concentrations are equal will be at this very specific concentration. And so then if we vary from that with more H plus and less OH minus, that would be acidic and would give us a pH of less than 7. And if we vary from that to having less H plus and more OH minus, that would be a pH greater than 7. Okay, and so this is kind of just reiterating what we talked about a second ago. The lower the pH, the more acidic. The higher the pH, the more basic. But a few extra things here. The pH scale, the way it works out, a single unit, so for example going from 5 to 4, that corresponds to an order of magnitude difference in the concentration. So that's a factor of 10 difference in the acidity. So if you're going from a pH of 5 to a pH of 4, that's not actually a small change. It's less significant than it is down here. Going from 2 to 1, the overall number of acidic molecules is larger going from 2 to 1 than it is going from 5 to 4. But in terms of the relative magnitude, it's actually the same. It's an order of 10. It's a factor of 10 difference from one to the next. Normally, when we're looking at the pH range, we only show it going from 0 to 14. But in reality, it can go beyond that. In terms of stuff that occurs naturally, though, it's going to stick between those two. I don't know of any naturally occurring situations where you would have a solution that is lower in pH than 0 or higher in pH than 14. Now, we can make solutions like this, and I have a lot of solutions actually in the lab that would have pHs in the negative range or pHs 15 or 16 even. But they're very rare to need to use. It's very rare to need a solution that is that concentrated for a reaction, and they're very dangerous as well. So we tend to avoid them. Okay. So let's calculate a couple pHs here real quickly. So the first one that we're going to do is 1 times 10 to the negative 12. Now, I know, just right off the top of my head, based on what I said earlier, since the first number here is just 1, I know this is going to end up being 12. But let's go ahead and do the math anyway. So if we plug this in to the pH equation, it tells us the pH is the negative log base 10 of the concentration of the hydronium ion, which is 1 times 10 to the negative, oops, I should write that correctly, not negative 2, negative 12. And so on your calculator, you should have a log button, and it should say log. So what you're going to do is you're going to put in the negative sign, hit the log, and then 1.0 e, so that's the engineering exponent to the EE button, if you have that on your calculator, which will take care of our scientific notation. That E represents times 10 raised 2, and then we're going to do negative 12. And that does indeed give us 12 as our pH. Is that acidic or basic? It's very basic. And not in the, dissing someone, ya basic type way. No, this is basic in terms of the chemistry. So then the next one here, 5.6 times 10 to the negative 6, that I cannot do in my head, but I believe it'll be something around 5, 5.5, something like that. Let's see if I'm right. So the pH is going to be negative log of 5.6 times 10 to the negative 6. So if we plug that in, that is not quite 5.5. 5. Ooh, that looks like a 6. That's not supposed to look like a 6. 5.25. One quick note, by the way, on Sig Figs with the pH scale, and with any log scale, actually. I'm not a huge stickler on Sig Figs, just to tell you this up front. I know I've mentioned this before, so if you're just off by 1 or maybe even 2, depending on the situation, I'm not going to bother with counting you off. If you're off by 4 or 5, though, I'm definitely going to count off. But when it comes to Sig Figs with log scales, only the numbers after the decimal point count. So actually, technically up here, this should have been 12.00. I should have included that because the numbers before the decimal point don't count for Sig Figs. So the 1 and 2 here do not count. This is like the only situation that we will ever come across where a non-zero digit does not count for Sig Figs. And this is just a result of the fact that this is a log scale, and the numbers before the decimal point are essentially just telling you where the decimal point is in a number. They don't actually add to the precision. So again, I'm not a big stickler on this, but I do want you to be aware in case you take a class after this and someone is a big stickler. I want you to be aware that only the numbers after the decimal point count for Sig Figs with log scales. Okay, let's do one more here. Let's calculate the H+ concentration of a solution that has a pH of 11.8. So if the pH is given, and we want to find the concentration of hydronium, we're going to need to do an anti-log, which is to say we're going to raise both sides, let me back up. We need to raise 10 to both sides, because we need to get rid of this log. And to get rid of a log, you do an anti-log, which means that you're going to raise both sides. You're going to have both sides be the exponent for the base of the log. So because this is log base 10, that means that we're going to raise 10 to both sides. Not only that, but we're going to take the negative that was over here, and we're going to move it over here, because when we raise 10 here, we're not actually getting rid of that negative there. So we're actually going to move that negative first. I should have mentioned that first, actually. So we're going to multiply both sides by -1. So we're going to have negative 11.8, and then just the log of h plus over here. If you forget to move that negative sign, you're going to end up with a huge number. And that should be a hint that you did something wrong, because the concentration cannot, it's actually physically impossible for it to be as large as you would get. So I'm going to use my anti-log button on my calculator. 10 raised to the negative 11.8. And it tells me the concentration of hydronium is 1.58 times 10 to the negative 12. And that would be a molarity. If you forgot the negative there, you would get 6.3 times 10 to the positive 11, which, I don't know, that might be even more concentrated than a neutron star. That is, as far as I'm aware, physically impossible to have a molarity that high. Maybe a neutron star could, but nothing else. Other than black holes, I guess, but those are infinitely dense. Anyway, so that is how we either find the pH given the concentration, or we can find the concentration using the pH. You can go both directions now. All right. I think I'm going to, I'm going to leave it there for this video. So in the next one, we will talk very briefly about some other P scales, so the POH and the PKW, which the PKW is not actually a scale. It's just a single number. But we'll talk very briefly about that, and then we will talk about how we measure the pH. So I'll see you in the next video.